All right, so it's always a tough act to follow after Jim, and I have the longest talk this afternoon session. But hopefully this is a good mix of applications here. It's not just one particular model or simulation, so hopefully we can keep the interest high here. With that, I guess I've met a lot of people on and off here. We've been talking about these application models. I guess the first question as a good engineer we need to ask ourselves is, what is an application model? Or in particular, what is a Barracuda Virtual Reactor application model, right? In its most simplest form, what these are sample cases that our staff has set up. So what we do is we typically do a literature search. We pick a problem, we do a literature search, we find some good papers, we take the information from that paper, and we set this model up in Barracuda. Once we set it up, if possible, we try to validate some of that, and then we sort of write a mini report, we host it on our website, and then we provide you with that simulation file. That's what this is about. All right, so, and hopefully towards the end of the talk, I'm going to actually open up the website and show where this is located exactly. The next question is, why do this? Or what's the benefit to our user community from doing this, right? So I guess, again, as engineers, when we see publications, in general CFD publications, the idea is that somebody has actually done these, right? So some part in the world, somebody has used CFD, and this particular problem can be solved using that. Then, we have some case studies where users have actually used Barracuda to set these things up. So then that, okay, fair enough, this can be done with CFD, now this can be done with Barracuda. Application models is where you are like, fair enough, now can I try doing this on my own, right? And that's where I think this actually gives you sort of more than a starting platform. You're not starting from scratch. You have something, a sample case set up in Barracuda to go start with, and that's what this does. Generally speaking, as you can imagine, right, as we continue to build these application models, these can act as like demonstration cases. That could be CPFD demonstrating. That could be our global resellers or global channel partners actually helping out showcase their customers what the tool can do. And then beyond that, right, I mean, if you think about it, these are fully set up cases. So if you have young users at your organizations who have gone through basic training, maybe even have tried advanced training, then you can actually download one of these files. And then, the key idea is, can you pick up some best practices down here, right? Or maybe you want to implement something that you're not quite sure how that can be done. That's not usually covered as a part of your training. You have an example case. If you figure it out and it's great. If you can't, reach out to us through support. We can help you do that. All right. And then, like I said, lastly, this is more than a starting point, right? Sort of a good base for a lot of the users to start off with. So the way I see this is basically we're translating our software features into action here. So what I mean by that is we are bridging the gap between what the software can do and what the user needs to do. That's the idea behind these application models. Okay, with that quickly, and I'll spend some time actually looking at, showing one of these posts. So in general, what you'll find is on a website, if you open up, generally you'll have an overview of the application, some description about the model and which paper we have taken it from. Obviously, most of the times if you have reactions in the system, we do explain them out. We do even to the level of like a reaction constants as well as the reactions themselves. We spend some time explaining the results, and then finally, give you some modeling instructions, and then the support files available there. I think we did do post-processing instructions in some of our older posts, but now with TechPlot layout files getting more modern, more repeatable, I think going forward you'll see a lot of layout files being uploaded for these post-processing. Okay, with that, let me move quickly here. All right, so what I've lined up today is a few topics here. So I'm going to actually talk about a few application models under hydrogen production. There are three of them. The solvent-enhanced methane reforming, dry reforming of methane, and then the molten metal bubble column reactor. I'm going to slightly switch the order here. What I'll do is I'll quickly walk through maybe my presentation and then do the demo in the end where I'll actually open a website and show you an application model. But then I think this is really of great interest to me because I have a background in upstream oil and gas. So lately, I would say in the last 18 to 20 months, we have actually had several users. We have several new companies actually from the upstream side of things using Barracuda for liquid solid flows. So I'm going to demonstrate a few cases in that as well. Okay, very quickly for hydrogen production. steam methane, again, at least in the recent few years, you saw a lot of emphasis of hydrogen being sort of a critical energy carrier. And if that's the direction we are taking, we want to make sure that how can we reduce the greenhouse gas emissions associated with producing hydrogen, right? And I think the picture here demonstrates that. Typically, any kind of methane reforming, it falls into gray hydrogen. If you can capture that carbon either during combustion, post-combustion, that's literally blue hydrogen. And then green hydrogen is where you're not producing CO2 at all, right? So you're either producing methane from pyrolysis or from electrolysis and so on. So in that line here, the first two examples I have fall under this blue hydrogen case. And then the other example that I'm going to walk here is the methane pyrolysis example, sort of falls in the green hydrogen case. Okay? And again, a lot of us down here have used Barracuda, so you kind of know the advantages. But if I can summarize it, I think from ground up, our solver was built to be a multi-phase flow solver. It's unlike other CFD softwares, which started off as single-phase flow, and then you threw in multi-phase as time went on, right? So what that means is because the solver, the inherent architecture is tuned for something like this, you're not only solving the hydrodynamics, you can couple them with basically heat transfer, reactions, all of this. So every time step, essentially, you're getting a couple solution from all of these. And to be able to do this fast enough through GPU acceleration is what sets us apart to be able to do these applications. Okay, all right, SESMR. Very quickly, I think this particular reactor, it's a pilot scale reactor. We did 2 simulations in this case. In one example, we ran just the SMR, that's just a steam methane reforming, and then we threw in some sorbents into it to capture that some of that CO2, right? So I'll show you 2 examples there. This is based on the work published by Johnston. Again, a lot of us know what I just described in terms of Barracuda Virtual Reactor solution is what I have down here. Value of simulation in an example like this, right? Obviously, test out the model, validate it with experimentation on your pilot scale, lab scale reactors. Once you feel confidence in the model, before you start scaling up, you can deploy your model first, get some answers, make some smart decisions as you go on. An example like this, what you're trying to do is you're trying to maximize yield of hydrogen, and so therefore you can plan around your operational strategies and how much catalyst to put in, how much sorbent to put in, and so on, right? Again, before you actually test these out, you can play with these things in the model. All right. Again, I don't expect you to read all the reactions, but I'll point to the main things. Firstly, this is a 1,000 millimeter tall reactor. The bed height is about 300 millimeters, and you have, I believe, 100 millimeters in diameter. Okay. As far as the reactions are concerned, you have a couple of these main steam methane reforming reactions, methane reacting with vapor here. Then you have your water gas shift reaction that happens with this. If all these 3 would form your steam methane reforming, if I throw in this carbonation reaction, right, with a calcined dolomite sorbent here, that's what actually is capturing your CO2 to produce a byproduct from that. And then typically, reactions, some of these expressions can be complex, especially if you're a new user, if you haven't used them a lot. So we do provide these, and then we also have some instructions on how you can input these within Barracuda. And then this is, the discrete carbonation reaction is actually implemented through a user-defined expression. Sam actually showed that earlier today. And so we also have a screenshot of that, and we explain how that is being set up. All right. With that, a couple of quick results down here. You're seeing, this is basically your steam methane reforming. I'm showing you dry mole fractions of CO2. You can see that as time goes on, as the reaction goes on, you're producing a bunch of CO2. But when you throw in sorbents, that CO2 is getting captured, essentially. So you're not, the CO2 is not going out of the reactor. Can we do some quantitative comparisons? Yes, we can. I've got a plot here, temperature, dry mole fraction. These dots all here are for your steam methane reforming. This is for your sorbent-enhanced case. The black dots are from Barracuda. And all the other dots are essentially a combination of experiment and CFD results. Okay, so decent confidence. Maybe we can try using it for scaling up. All right, next example, it's very similar. The reactor setup is quite similar, but I think you heard Dr. Reddy talk about how in his yesterday's talk, right, he was mentioning about how capturing CO2 is becoming more and more important. A lot of oil and gas companies are actually investing there. You could capture all of that CO2, store them, that's good. You could also use some of that CO2 with methane and actually convert that into syngas. And that's what this example walks through here. So again, a very lab scale set of reactor. In this, again, the reactions change. So you have the main reaction, which is the dry reforming of methane, reacts with CO2, produces hydrogen and CO. You want to suppress your reverse water gas shift reaction in this case. So, that could be a function of how much catalyst you have, the temperature at which you're operating, things which you can easily test through simulations. And so that's what we end up doing, right? So if you look at this example down here, what I'm showing are mole fractions of hydrogen in here. I'm showing mole fractions of CO here. And you can see that we're getting more than 1 ratio of H2 to CO, which is kind of what you want to do with these cases. Again, is it a simple lab scale setup? Yes, it is. But again, as you sort of take it and adapt into your into your own systems, we provide all references down here. We provide these reactions. You have a starting point. All right, this one's my favorite here. This actually shows one of our unique capabilities here, where now we have a bunch of bubbles primarily, right, coming into a molten metal bath. So this is actually one of you see across the world where a lot of people are actually looking into methane pyrolysis by injecting methane into molten tin baths essentially. So what happens is basically you sort of break down the methane and you end up producing some hydrogen and then some solid carbon, right? And that rises to the top of your molten metal bath. The physics is extremely challenging. The reactions make it even more harder. What we're trying to do in this case is, again, it's based out of a paper, no here. We are actually just solving the hydrodynamics in this case. We don't have reactions included. But again, that gives a lot of information, right? Because the bubbles in this case, they can break up, they can coalesce, they can grow in size as they move up. And as you can imagine, right, the reaction rates are driven by the surface area in contact with the bubbles and the molten metal. So even understanding the hydrodynamics can help you quite a bit in terms of planning some of these, or just understanding how your reactors are behaving better. All right, there are a few interesting things I want to point out in here. Firstly, in this particular case, in our example, we basically have about 10,500 cells. Oh, and this is a molten ferrous bath, and we're injecting argon bubbles in this. Barracuda simulation has about 10,500 cells. The paper that I'm following here uses a VOF model. It had 5 million cells in its case. Now, because this is a Lagrangian, the way the bubbles are tracked or modeled in Barracuda are Lagrangian, there are a few inputs that need to be provided. And as you can imagine, right, you have to sort of start off with a good guess for your initial injection bubble size. You need to know what the maximum size your bubble can grow so you can cap it off. That's an input to give to the software. And then another factor that goes in is the coalescence factor, right? As these bubbles move, if they grow, what is the probability of them coalescing and growing together? Now, how do you get this information? In this particular application model, we show you how we got that information from some of the papers published. So for example, the maximum bubble size limit, right? I've estimated that based on the paper, based on the work of Irons and Guthrie. Now, you don't have to do that. If you have an in-house CFD tool, with VOF, you can run one single simulation, right, at a given flow rate, figure out what the max bubble size is, and then you can carry it out into your subsequent simulations. Bubble departure diameter. In this particular example, I am showing a relationship published by Islam, where it relates your, the bubble departure diameter with respect to the orifice diameter. You can use this relationship. We have got a plot here with the data, or you could again run a simple VOF simulation, get that value, plug it into Barracuda, and then change the conditions and get hundreds of such cases run very quickly, right? Again, some interesting results here. Obviously, pretty pictures here. The bubbles are being colored by the size here. The average size coming in is about 11 millimeters. You see some shearing off due to turbulence and near the inlet or the injection points, the bubbles do become smaller, but as they move up the molten metal bath, they grow in size down here. Again, can I compare some of my published data? I've tried doing it. Firstly, the mean bubble diameter down here as a function of flow rate. So some of those tuning parameters I showed you, I tuned them for one particular flow rate case, and then I tested the Barracuda model for other flow rates in this example. And we do a decent job matching some of the data down there. Again, it's a mix of experimental and simulation data in here. I also compared the drag coefficient on the bubbles, with respect to the bubble Reynolds number. And again, we do a decent job. I think the bigger takeaway, though, from this simulation is that the simulation that we have run in Barracuda runs within a matter of hours. Whereas, again, this paper published in VOF, it's an older paper, but it took the authors at least on the order of days here, 2 to 3 days to run one simulation. So, if you can imagine, you get some of those initial parameters from your VOF simulation, you run a whole range of cases down here, and one of the most, use cases we are seeing go, a lot these days is especially with Barracuda, is the acceleration that our solvers provide to, and which helps us to solve these problems quickly, also helps you generate training data for your raw models. So, one VOF simulation, tune the Barracuda model, run hundreds of these, get the training data, use Saurav's model, and generate a ROM on this, right? So this is a great example of that, of how you can, combine multiple simulation tools and get your answer. With that, like I said, I'll do the demo in the end. I'm going to switch to my favorite topic down here, which is liquid slurry flows in oil and gas upstream examples. So, again, if you put aside the controversy around hydraulic fracturing, it is important to know that hydraulic fracturing is the primary mode of production of oil and gas in the United States currently, right? More than 75% of your natural gas and 48% of your oil production is currently done through hydraulic fracturing within the States. And this particular methodology, fracking, which I'm going to explain in a second, is used over in more than 95% of your new wells. And this is a multi-billion-dollar industry all over the world. So any kind of insights you can provide, optimization you can provide, goes a long way in terms of the dollar amounts that are associated with something like this. So for those who may not be familiar with what fracking is, this is actually just a schematic of how a drilling rig looks like. You have a drilling rig. This is your pay zone where you have your oil or your gas. You want to extract that. You start drilling a well vertically down there, and then once you get to your pay zone, you start going horizontally, right? Pretty much, majority of the wells right now, because all the easy oil is gone, if you have to reach the difficult zones, then horizontal drilling is the way to do it. And these, it's tough to imagine, but some of these horizontal wells, they can extend hundreds and hundreds of feet, and you can have multiple of these wells going and hitting these pay zones. Fair enough. Ideally, once you drill the hole and you apply suction pressure, oil should flow into this wellbore, and it should move up. You can imagine that in some formations, though, like shale formations, which they do not have interconnected pores, so oil is not able to freely move through those pores and reach this wellbore. What do you do, right? You provide those fractures. You provide those connections. How do you do it? You pump in high-pressure fluid, which is essentially water mixed with some kind of polymer. It's called slick water. It's highly pressurized. You pump it in. You initially create blast some perforations, literally blast them, and then you pump in this high-pressure fluid through that, right? And you can imagine it creates hundreds of these or thousands of these fractures essentially into the shale formation. And then once you do that, you provide sort of that interconnected pathways for the oil to flow through. But is pumping liquid just good enough? Apparently not, right? Because you have got hundreds of feet of earth on top of it. So how do you keep these fractures open? You pump in proppants. Proppants are literally solid particles. They could be as simple sand. They could be highly customized coated material as well. So essentially a whole bunch of solids that you're pumping in. You're hoping that all these solids settle down in these fractures. It's literally a filling problem. You're hoping it fills as far as it can, as much as it can. So you prop open these fractures and you produce oil from them. All right. So again, like I said, because of how expensive some of these oil wells are, drilling them, fracturing them, and then keep on producing them for a long time. Any sort of insights you can give into how you can improve the distribution of these solids into these fractures, actually goes a long way, right? If you increase well productivity, if you can keep the well in operation for a long time, that is gold dust. And CFD, just like many other things, I mean, it's, as you can imagine, you cannot see what's happening downhole. You can do some simple tests, plexiglass tests, and you can see how they fill in, and I've got an example where we validate that. But downhole, you can't put cameras, you can't put sensors, it's just too hot. And then therefore CFD acts as a great visualization tool as well. All right, I've got a simple example case here. This is actually a lab case that is 4,000 millimeters in length. It's about 300 millimeters tall here. I've got a 10-inch thick fracture down here. And again, this is, as I was saying, right? Imagine you come down that horizontal path, and this is actually sort of how it's extending into the rock. This is sort of your fracture that you have just created, and now you want to see if I release some solids along with the slick water, how far are these solids going to settle down, essentially. And the further they settle down, the more area they occupy. That's the area through which you'll be able to produce oil. One thing with the slick water is it is non-Newtonian in behavior, so you have to start thinking about non-Newtonian drag models. Then, obviously, the proppant, this is a 40 by 70 mesh here. I've shown the PSD here. And again, you can have 100 mesh sand, and then you can also vary them. For the first 10 minutes, you can pump 40 by 70. The next 10 minutes, you can pump 100 mesh sand, right? Typically, these are decisions that a completions engineer sort of makes before you sort of, plan for the job, and any, again, insights that simulation can provide would be quite helpful there. All right, so as I was pointing out, the slick water, it's a mix of regular water with some polymer. It is non-Newtonian in behavior, so your drag model also has to account for. In this particular example, we're using a simple power law. So your shear stress is related to your strain rate down here, right? In a Newtonian fluid, you do not have this N, non-Newtonian, you have N here. And typically, in such cases, N would be less than 1, right? Shear thinning fluids, which is what this is. Okay, so here's a nice animation down here. Let me break it down for you. So like I said, I am injecting slick water along with proppants. What I'm showing in the plot down here is particle volume fraction on the top. Obviously, the darker it is, the higher the volume fraction there is. This is quite a polydispersed system, so the packing volume fraction is slightly on the higher side here. But you can clearly see, and again, this simulation has been tested out till about 1250 or 60 seconds. So with time, the proppants settle down, and you can see sort of this mound forming. And towards the top, though, you start seeing some shearing off, essentially, of the proppant. It's trying to go further and settle down. Now, if you look at what's happening with the particle size, you see that a lot of the larger particles are actually settling down, which is what you want, right? You want some of the larger particles to settle down and pack completely till the top of your well down here, because this is a region where you're going to pull oil from, so you want to pack it as high as you can. But some of the lighter proppants, right, or some of the smaller proppants, you want them to settle down further. So that's why you have a PSD, and you can play around with multiple sands down there. You can plan your job, first 10 minutes this size, next 10 minutes the other size, I'm going to change the flow rate, and so on. But that's the idea. You want to fill these solids up with different sands, and the greater area you can keep filling, that's going to be your production zone. Lastly, we can also look at residence time of these proppants, right? So proppants which have been injected at the beginning are the ones which are settling down. With time, obviously, they can't settle down here anymore, so then they start moving towards the end of the fracture down here. Okay, I've got some data here again, and as you can see, right, this is a consistent theme. Where we try validating our software with published results. What I'm showing down here are 3 curves. Each one of these curves is at a separate time. I believe this is around 300 seconds, 600 and 1200. Excuse me, my eyesight is not the same anymore, so I might be misreading those labels there, but roughly around those times. Obviously, the symbols are from the experiment down here, and what I'm showing is the length of the fracture and the bed height here, right? So with time, obviously, you're packing up more particles, so your bed height changes, and that's what I'm showing down here. Can I quantify this further? yes, I can look at the area under the curve, and I can see what the total amount of mass, or in this case, the area under the curve between these is, and compare that between experiment, which is in gray bars, and CFD. Again, we see a fairly good match between both of them. All right. So one interesting story to say here, though, as you watch this animation play again. So we had we actually had a major oil and gas company actually approach us for this example. This was about 18, 20 months ago. We were just setting up this prop and transport model, working on this application model. And the customer reached out to us. They were actually trying to do something similar here. They had a small lab scale fracture that they set up. They were running CFD simulations. And guess what they were trying to do? They were trying to create a ROM model based on that, right? So they wanted to do hundreds of CFD simulations, create a ROM model out of that, such that once that you have a well-trained model, then they can use it for their field planning job, right? Essentially, so you give it in the hands of a completions engineer. He wants to quickly test what happens if he changes his pumping rate or changes the proppant size. How far are my proppants going to settle down? You want that answer within seconds. You don't necessarily want to wait for days, right? As you're planning these jobs. So that was the idea down there. You will see that consistent theme across many of how examples and how these ROM is going to be used. So the customer was using another CFD tool. They had good success. They were matching data, but their experimental data, but it was taking them about 5 weeks to match the data. Whereas we were able to run these simulations within 4 to 5 days within Barracuda. And guess what that does, right? As I was saying in the other example, if you have a decent enough solution with CFD down here, you can run hundreds of these cases and then train your ROM model. So a nice real-world example for where you see all these things are headed towards. Okay, with that, now fair enough, we have showed enough lab-scale models. Can we take this and simulate something which is field scale, right? Field scale means a few things. Firstly, the domains are longer. You have more than one fracture. Usually you have hundreds of fractures in a pad. But in this example, we are studying a placement of proppant in 3 different fractures, and I'll show the domains in a second. The key idea is that another decision point that many of these oil and gas engineers have to make is, I have these tens of these fractures. How do I space them? Do I space them 5 meters, 10 meters, 15 meters, right? And then once I space them, then I figure out, do all these fractures grow equal in size? Turns out they don't all grow in equal in size. So there are a lot of complexities around it. So for that, we set up 3 cases down here. As you can see, these are multiple fracture domains. So like I said, each one of these rectangular fracture, it's an idealized domain, but still, quite close to reality in terms of, the dimensions here. So we have 3 fractures. The key difference is the spacing between the 3 models. In the first example, the spacing between the fractures is 5 meters. In the second example, it is 10 meters. And the third example is 20 meters. Another thing you see is that the middle fracture, right, it's quite short. In the first case, it's slightly longer, and it's almost as big as the other 2 fractures in the 20-meter spacing. So what's happening is, when the fractures are placed too closely, you can imagine there are stresses in the rock. It's called a stress shadow effect. So that's applying pressure to the adjacent rock down there. So the middle fracture doesn't grow in the same size as the other 2 fractures. And this is something that does happen in real world. But if you give enough spacing, all 3 fractures can be of equal size. And you want that, right? You want your fractures to be equal in size, such that you can hit your pay zone well there. Again, there are a lot of dimensions here, but key takeaways are, you can see that the domains are hundreds of feet, right? About 200 feet in length, we're talking about. At the same time, if you look at the scale disparity, the thickness, these are tapered rectangles. Those start off at 1 inch thick, and they're tapered off to 0.4 inch thickness. So the disparity in the scale itself down there. And then again, there are different dimensions, as I said, as for all 3 cases, in terms of lengths and tapering. Okay, all right, again, we have a PSD of the proppant that we're pumping in. We are going to test 2 different cases down here. We're going to test 30 barrels per minute and 45 barrels per minute. The well toe end is closed. What you're saying is your fracture has tapered off well enough, and at that point, essentially, only liquid can leave, not necessarily any particles, right? So that's what I mean by well toe end is closed. Sorry, my mistake. The proppant fractures are open, but the toe end of the well is closed, and I'll show that in a second here. Okay, so this is again 40 by 70 mesh sand, and this is the key I was talking about, right? We were actually able to run about 20 minutes worth of simulation time in about 17 hours using one of our fastest GPU cards, compared to what some of the other simulations that our customer was using. It was roughly taking them 4 to 5 weeks to do some of these simulations. Okay, all right. We move on quickly. This is an animation that should play. All right. As you can see, again, I'm showing you prop and volume fraction, all different spacings here. Just visually, you can see that, obviously, the first fracture, it gets a lot of propant. In the 5-meter spacing, the middle fracture gets decent amount as well. But the third fracture is kind of starved. In this 5-meter case, it becomes worse as you increase your spacing. And in the 20-meter spacing case, the third fracture is not getting any propants. So once you stop pumping, that thing is going to close. Okay, and that's what I'm explaining. Can we quantify this a little further? We can try to do that here. What I'm showing here is the total amount of mass of propant, plotted as a percentage. Propant that goes into your first, second, and third fractures. Blue is 5 meters, orange is 10 meters, and 20 meters is green. So as you can see that as I change my spacing, as you were visually seeing, essentially in the 5-meter spacing case, the first and the second fractures were getting decent amount, but as you increase the spacing, most of the propant mass is going into your first fracture, right? And why is that happening? In the 5-meter case, as I said, this stress shadow effect acts as a back pressure, and you end up getting, that's actually forcing sort of, forcing more slurry to sort of go downstream there for you. Whereas when you start having wider spacing, essentially your friction losses in your pipe make it harder for the propants to essentially travel down into your second and third fractures, right? Okay, fair enough. This is the problem at 30 barrels per minute. If I increase my flow rate, can I actually see more propant getting into the last fracture, right? I'm looking at the 10-meter spacing case, 30 barrels per minute, 45 barrels per minute, and it turns out, yes, as I pump at a higher rate, I'm overcoming some of those friction losses. So therefore, now I can start getting more propant into my third fracture compared to this case down here. Similarly, I can try quantifying this. Again, the blue is for 30 barrels per minute. The magenta down here is for the 45 case. You see for the 45 case that I get more propant mass going into my second fracture here. Again, third fracture, it still doesn't get enough propant down there, but there are other ways that you can solve that problem. I'm not getting into in this example, but currently you have your horizontal wellbore here, propant is coming in, it makes a 90-degree turn and settles in the fracture, right? So if you can imagine right now the north, south, and sort of the west faces are open for the propant to go in, but I can do what is called limited entry. I can close and open valves literally down there, and I can then create additional pressure, and as you can imagine, I can pump more propant downhole or down into the third fracture. Okay? And that is something we have done as well, right? And again, all these little variations we're talking about, these are not simple, sort of academic variations. These are actually what is done in sort of real world here. All right. Lastly, I've got an interesting topic here. This continues on the line of examples I'm showing with upstream applications here. So now this is on the other side, right? Fair enough. I've drilled a well, I pumped in propants, I've settled them down, propped open, I can start producing oil. But you can imagine that as you start producing from one of these wells, some of those propants can start flowing back, and then you also have natural formation sand that's present in the rock that can also start flowing back. Now, sand, liquid at high speeds is not a good thing, right? It essentially starts eroding away your metal equipment. And then, if you erode a lot of sand, sometimes you can collapse your rock formation. That leads to a complete loss of your well. Again, loss of well runs into millions of dollars. So there's a lot of sand mitigation strategies that these companies plan around, such that you can keep producing oil at decent enough flow rates, but can you stop producing some of these sand particles? Fines are producing sand fines are okay because sand fines are suspended in your liquid and they get transported. But how do you do that, right? A classic example, as you can imagine, is a screen, is a filter. And they call it a sand screen filter down here. So the idea is, you essentially, you have your well. Once your well is completed, you cement your well, you create some perforations, you put a sand screen down there, and the idea is that this sand screen blocks away majority of your sand particles here. Typically, you can imagine these slot widths are quite small. They're about 100 to 250 microns in size, compared to the domain size, right? These, as I said, the lengths of these wells can be hundreds of feet. But even on a decent CFD case, right, if you were to model a 1 meter length section of your sand screen or 9 meter section, the disparity is quite big. If you're trying to resolve each individual slots in your screen and then still grid all the other, the domain itself, you're running into millions, if not billions of cells. So quite impractical to do. And that's where we have a nice feature here. Again, interesting thing about this feature is, our users have used baffles for over the years, typically thermal baffles and so on. But we have found another interesting use for this feature is use a baffle as a filtering device, right? So essentially what we're saying is this entire screen is going to be modeled as a baffle, such that the baffle can filter out particles. And how can it filter out particles? Well, it turns out we added in a feature for this. So now, when a particle hits this baffle, actually, we can define a size-based passing probability. So if the particle is of a certain size, it has a certain probability to pass through the baffle. And again, an interesting story here is that we were working with again, another customer in the upstream side of things. Again, they found this baffle approach quite nice. This, again, running simulations quite fast. They were able to get good answers from this simulation, but they wanted this feature, as you can imagine, right, where in reality, the slots only let a few, block particles of certain size, let particles of certain size through. So they were asking us, can this baffle model be, sort of have additional features that can actually replicate real-world behavior? And it turns out, nice thing with this was they ended up paying us for what we're doing down here, so we were able to actually implement this feature into the model as a turn for this example, right? So again, a great example where we're working with these application models. We see some interest from customers. They like what they see, and then potentially there's some funding involved in there, and some of these features also get input into the software through those means. So, okay, with that. Very quickly, I'm going to show you how the baffle or the tool looks like here. This is a section of your wellbore. So all the red down there, you can imagine sort of that's like the interface between the rock and your hole, if I may say so. That's the wellbore. And so the flow is going to come radially in, right? As I show in this cut schematic, flow is going to come radially in. It has to pass through this orange color screen. Hopefully it's easy to see this. This orange is what the sand screen is, and we're modeling that as a baffle. So once liquid particles come in, they get filtered at this baffle, and then they have to make it through the holes in this base pipe. And once they make it through, they get produced, right? And this is the horizontal section, and they would move all the way to the top. Now, this baffle, we can be tuned to represent different types of screens. As you can imagine, there are a lot of different types of screens. For example, a wire wrap screen, you can have an oven metal mesh screen or a premium screen and so on. All you need to do is basically you have to tune your particle passing probability to a given type of screen, and then the baffle then sort of mimics in some ways as to how that screen behavior looks like. How do we do this? There is some published data. Typically in literature, you would see some screen filtering based on, it's called sand retention test data. So essentially, you put a heap of sand particles over a mesh. Either it's due to, you drop some of these particles with gravity, or you're letting some fluid flow through that. You do some experimentation. You can do some DEM. You can see how much sand you're producing, the inlet PSD, and the kind of PSD you're producing. So if that information is available, we can tune a probability based on that. Okay. And here is sand PSD again, just like proppant PSD. This time we have sand PSD. But another thing on top of this is this passing probability for the baffle. So based on the size of the particle on the x-axis, I have a probability value. So in this case, I'm saying roughly anywhere between a 0 to 120 microns. my passing probability is 25%. So 1 in 4 particles essentially makes through, right? And then because the screen size I think is about 250 microns, so more than that particles can go through, so the probability doesn't exactly become 0, but it's quite low as the size increases. All right, and I've got some nice animations here. I'm showing you the cross-section cut as I was showing in the previous slide here. You have radial flow coming in. It's taking some of these particles. What you're seeing is 2 views of the same simulation. The difference is the particle size. Between 0 to 125 microns, what I've done is I've blocked or I've blanked all the particles which are greater than 125 microns in this case, right? So you're not able to see them. So you can, and therefore you see that particles in this range are being allowed to pass through by the baffle, and they are being produced. Whereas in this case, particles which are greater than 125 micron, as I said, the probability drops sharply, so you end up producing just a few of those particles here. Can I quantify this further? As I said, right, people typically look at what the inlet PSD of the sand is from those sand retention tests, and you're looking at what is the PSD of the sand you're producing. And so the nice thing with Barracuda and TechPlot is you can script up something very quickly in Python. We give you a lot of raw data information of particles and fluid, and that's what I ended up doing down here. Got some of the data. This is the inlet PSD we're putting in, and this is the outlet PSD. And this is exactly the kind of metrics that let's say somebody in the completions department is looking to get. You want to know what the outlet PSD is. As long as you're producing a lot of fines, that's okay. They will get suspended with the fluid because this is not gas, right? This is fluid. They get dragged down to the top, but you have heavier particles. You can start eroding away some pretty expensive equipment here. With that, I come to the end of my presentation. I'm going to switch modes here. I'll quickly show you this application model page. All right, nice. Okay. All right, so if you have not checked out our website, this is our website, cpfdsoftware.com. Under this, we have a segment for resources. So if you click on resources, you see application models. That's what we've been working on over the last several months here. And under this, you will see a whole list of applications, right? We have an application model for TRISO that Keshav is going to talk about today. We have an application model for industrial case CFB that Tanner will present today, right? And then we have a couple of application models on the cement industry, calciner, conditioning tower that Pramod will present. So again, right now, these application models cut across segments of industry, different applications. As we add more of these, we'll start having subsections, upstream oil and gas, here are applications, cement, here are application models under that. But the nice thing about these is anybody can open our website. Let's say I want to look at this sorbent enhanced steam methane reforming, right? I can click on this learn more segment here. And as you can see, we start up with this landing page here. It gives you an overview of our application model. And then you have some hot links down here that will take you to different segments. But let's say I want to look at the entire segment here. I'm looking at this for the first time. I would click on access model. So far, I haven't logged into our website, right? As you can see, this is all out there in the public domain. You can look at this particular post down there. As you scroll down, you will see this example that I was talking about earlier. I've got a picture of that. I'm going to let the font load in here. Just a second. It takes a bit of time sometimes, so the browser is slow, but you should see those reactions not in LaTeX code, but in the equations form. All right, there you go. Okay, so you see these reactions here. We have listed them out. Same reactions I was showing on my slide. The good thing is we exactly tell you which literature we got these from here, right? And towards the end, we also give you the complete reference for that literature sources. So pretty much all of these, gas phase reactions are given here, but the reaction constant for the discrete phase reaction, right? Because that needs a bit more explanation. Towards the end, we actually explain that as well, how that was input into Barracuda. Some of the results, same results I was showing earlier here. And as you can see right here, there's a hot link for support files. Now, I'm going to click on this in a second as I show you the complete post and I come back here. But to download the support files, though, one needs to be a user or at least reach out to us so that we can help you get some of these support files. So you need to be able to log in to get access to that. All right, again, as you can see, we do a good job here. For example, rate coefficients, right? We take one particular rate coefficient, we exactly walk through how we have converted some of the units given in the paper versus the units that Barracuda needs you to input in, right? So we do that for one, and rest of them can be done in a similar format. And this is a user-defined expression down here. We clearly sort of show you how some of these went into it. We try our best to make sure we provide reaction units and so on, such that all the information is available for the users. All right? And again, post-processing instructions to create some of those plots I was showing in my presentation and on this post, right? How do you get them from TechPlot? Okay. And then towards the end, we have these references from where we have got this data. So let me go back to the support file segment here. Let me click on it. And I am actually going to log in as a user, not with my editor's login. It's going to be, right, let me do this. Okay, so now I just logged in with my personal email down here, access to this. I have got a zip file. I'm going to click on this zip file, and that lets me download it. So turns out I do have this download already, so let me go there. Here, so I have a zip file that I just downloaded. I have already unzipped it, and here is my file, right? Let me go in here, and let me open up my, my project file. If I can. Okay, there you go. Quickly here, okay, let me quickly walk through this. Obviously, more instructions are on the website there. We provide you with an STL file that we set up for this model. Obviously, the grid is generated. One thing you need to do is, because we do not generate these grids when we upload the support files, to keep the file size to be small. So do generate a grid before you run the model. Global settings, this is an isothermal compressible flow simulation. Material database is provided down here. We have them. We set up the model with the appropriate settings in your particle model down here. Again, you can imagine this is one of the older settings, so we're using Snyder model down here. But again, here is where I have my nickel catalyst material with a PSD defined. I have my dolomite as well here. And there was a question earlier, right? These are all group B particles, by the way, about this. Okay, so once this is set up, I'll show you a couple of interesting things down here, right? One is under this chemistry section. So if I go under rate coefficients, so these are all the rate coefficients we just looked at the website. These are all available here. You can click open on them, take a look at them, copy over into something else, and I'll show how to do that in a second. Reactions are set up down here, and then so once this is all done, all you have to do is come here and hit run solver. That's all you need to do. I mean, this thing runs fairly fast, but in the interest of time, I'm not going to hit run here. I've already done that for you. And once you hit run, it goes and it starts generating results like this. So if you follow some of those instructions given a post, you can post-process the results. I'm actually showing you a mass fraction here of CO, but you can also plot mole fractions. But essentially, all of that's available, right? The model is ready to go, hit run, get results, follow the post-processing instructions, and generate results on your own machines here. One quick thing I want to do is, before I leave, I want to show you how I can import chemistry into a newer model. Imagine I have a different reactor setup, right? It's not the same as this solvent-enhanced case, but all I care for is the chemistry here. Do I have to manually copy-paste? Hopefully, you're smarter than me. You don't have to do that. You can just import that from a project file down here. All I'm going to do is I'm going to say browse, go into this SCSMR section, check this project open, right? I have that project. So this is a nice feature about Barracuda. It's going to ask you, do you want to bring all the material properties in this case? Maybe I want to, maybe I don't want to. In this particular case, I just want to bring in the chemistry. I don't have any chemistry defined, so I'm going to say bring in all the chemistry and say append to the project file. So lo and behold, I go in here. I have all my reactions and my coefficients defined here. All right? With that, my talk comes to an end. All right, I can take any more questions. I think I'm short on time, so.
No, we have some time for some questions.